Exercise 3.2. Prove that the sum from k equals 1 to n of k squared, which means 1 squared plus 2 squared plus 3 squared all the way up to n squared, is equal to n times n plus 1 times 2n plus 1 divided by 6. And I've given a hint here as one way to go about this, which is the way I'm going to use. X plus 1 cubed is equal to x cubed plus 3x squared plus 3x plus 1, and that's for all real numbers x. And so we can let x equal 0, 1, 2, all the way up to n, and write out the results in rows. For example, the first row, when x is equal to 0, is going to be that 0 plus 1 cubed is 1 cubed, and that's equal to 0 cubed plus 3 times 0 squared plus 3 times 0 plus 1. And then at the end, conclude that we can find a similar formula for the sum from k equals 1 to n of k to the power of p, where p is a positive integer. Alright, let's give that a try and see what happens. Okay, so x plus 1 cubed, as we already know, is x cubed plus 3x squared plus 3x plus 1. And then let's write a little column here. So firstly, we'll use x. So x equals 0. That gives us 0 cubed is equal, sorry, not 0 cubed, 0 plus 1 cubed. So 1 cubed is equal to 0 cubed plus 3 times 0 squared plus 3 times 0 plus 1. Okay, x equals 1. That will give us 1 plus 1 makes 2. So 2 cubed is equal to 1 cubed plus 3 times 1 squared plus 3 times 1 plus 1. And then x is equal to 2, gives us 3 cubed is equal to 2 cubed plus 3 times 2 squared plus 3 times 2 plus 1. And we keep going. And then at the end, we're going to get, okay, not quite the end, the row before the end is going to be n cubed is equal to n minus 1 cubed plus 3 times n minus 1 squared plus 3 times n minus 1 plus 1. And then the last row is going to be n plus 1 cubed. So this one here was x equals n minus 1, and this one here is going to be x equals n. Okay, so n plus 1 cubed is equal to n cubed plus 3n squared plus 3n plus 1. Now you've probably already figured out what to do next. I suggest you pause the video and have a think about it if you haven't already. Okay, well, next up we just add everything together. And observe that if you add all of these together, you're going to get the sum from r equals 1 to n plus 1 of r cubed. And that's equal to the sum from r equals 0 to n of r cubed. So that's adding all of these ones together. Plus, and then all of these 0 squared, 1 squared, 2 squared, all the way up to n squared, all of these ones have been multiplied by 3. And so in total we're going to have 3 times the sum from r equals 0 to n of n squared. And then plus 3 times the sum from r equals 0 to n of just r. I made a mistake, silly me. Shouldn't be n squared here, it should be r squared. And then lastly, it's just, well, we have n plus 1, lots of 1 added together. So the last term is just going to be n plus 1. Okay, next up, we can observe that even though we started at r equals 0 for these three, it doesn't matter because when r is equal to 0, all three of them are 0. So we can just ignore the 0th term and start from r equals 1. So that's no problem. And then here's where the beauty lies. Because we have the sum from r equals 1 to n plus 1 of r cubed. And then over here we have the sum from r equals 1 to n of r cubed. And if we subtract from both sides, then on this side here, so let me just write that out, subtract the sum from r equals 1 to n of r cubed, and then over here subtract the sum from r equals 1 to n of r cubed, then that's just going to leave us with the last term in this series, which is just going to be the n plus 1 cubed. So on this side of the equation, we have just n plus 1 cubed. That's the result of this subtraction here, because all the other terms will cancel out. And then this just disappears completely. And then so we have 3 times the sum from r equals 1 to n of r squared, which I believe is the thing we are looking for. We're trying to find this one. Plus 3 times the sum from r equals 1 to n of r, and we already figured out that that's going to be n times n plus 1 divided by 2, and then just plus n plus 1. Okay, and then all that's left to do is just move everything to the other side. So we'll leave this part by itself on one side of the equal sign. So 3 times the sum from r equals 1 to n of r squared is equal to, let's get everything over 2, so 2 times n plus 1 cubed divided by 2, and then minus 3 times n plus 1 divided by 2, and then also minus 2 times n plus 1 divided by 2. Factoring out n plus 1, we get n plus 1 times 2 times n plus 1 squared, and then just minus 3n minus 2. This whole thing is still divided by 2. And then just expanding this thing out, it's going to be 2n squared plus 4n plus 2 minus 3n minus 2. The whole thing divided by 2. One more. I'm sorry, I'm always really slow with these. So it looks like n plus 1 times 2n squared plus n. So we can factor out an n. So 2n plus 1, and the whole thing is divided by 2. And so that was 3 times the sum from r equals 1 to n of r squared. So 3 times what we're looking for. And so that just means the sum from r equals 1 to n of r squared is equal to n times n plus 1 times 2n plus 1 divided by 6, which is exactly what it was supposed to be. N times n plus 1 times 2n plus 1 divided by 6. Now, we've almost finished this exercise, except we have at the bottom here, conclude that we can find a similar formula for the sum from k equals 1 to n of k to the power of p, where p is a positive integer. So we know we can do it for p equals 1 and p equals 2, because we just did it for p equals 2 over here, using this interesting expansion here. What about if we wanted to do it for p equals 3? Well, in this case, we could do exactly the same thing, except we could use, so p equals 3, we could use x plus 1 to the power of 4 is equal to x to the power of 4, and then it's plus 4 times x cubed, and then I think the next term is 6. 4 choose 2 is 6. So 6x squared plus 4x, and then plus 1. And then if we use the exact same trick that we used in the last one, notice that if we do it if we take x equals 1, 2, all the way up to n, then notice that all of these x plus 1 to the fourths will cancel with all the other ones when we go ahead and we add all the rows together. And so we'll just be left with 4 times the sum of, the sum of these numbers cubed, which is what we're looking for, and then plus 6 times something we already know, plus 4 times something we already know, plus 1. And then we just combine and simplify. So we can easily get it for p equals 3, and then if we wanted to get it for p equals 4, we would do the exact same thing again, except this time we would take x plus 1 to the power of 5, and then it would be x to the power of 5 plus 5, x to the power of 4, so on and so forth, and then we'll be, all of these ones will cancel out once everything is added together and we subtract it from both sides, and then we'll be left with 5 times the sum of all of these numbers to the power of 4, plus, and then some other terms whose sums we already have formulas for. So that will give us a way to get the formula when p is equal to 4. And so on and so forth. You can keep doing this forever, and you can get a formula for any positive integer p-value that you like here. Although those formulas might get pretty complicated after a while. Who knows? Anyway, in further math, we only need p equals 1, 2, or 3. So if you like, as an exercise, you can go ahead and derive the formula for the sum from k equals 1 to n of k to the power of 3.